Good evening, sir.
Good evening. So if you have any doubt, you can ask. Am I audible? Hello.
Hello. Yes, sir, you're audible. But I'm actually driving, sir, so I'll not be unmuting. That's
Okay,
why.
okay.
But thank you, sir. Thank you.
So we'll be starting in a minute. Okay, let the people join. So is my voice audible? I hope I am audible, right?
Yes, sir.
Yes, yes. Then we'll move. If you guys don't have any doubt, I will directly move on to the numericals on passive power filters. Okay. So this is the first problem that we have. That we have a single phase 3 branch shunt passive filter. The branch is designed to eliminate the third, fifth, and higher order harmonics. So we have one shunt for one phase designed for that is per phase. You have yes. Any doubts? Okay. So we have like this. So it is a three-phase system. So we have like this. We have the supply, and we have connected the shunt passive filter, and these are the elements. And then you have the loads and all those things, right? So what is happening that inside this passive filter, we have three branches, right? Like this. So one branch for the third, another for the fifth, and these you have high pass filter. And these are all connected to one, for example, phase A, right? Then for phase B, you have similar like this arrangement. So the third is designed to actually that it is an LC arrangement that we have done, and so like this you can see C3, L3, and R3. So we want to provide low impedance path to the third harmonics. That's why we want to minimize the impedance for that particular harmonics. So this branch is designed for that per phase. All the three phase have third harmonic branch. Passive filter, we have done it with passive filter. This arrangement is done. Then obviously for the fifth harmonic, we have again created one branch per phase, and the high pass filter is like this. So you have L in parallel with R and then C. So like this, the third branch. So this is a high pass filter branch that will absorb or provide low impedance path to the that is 7th, 11th, and all the higher order harmonics. So this one is designed for that, and these two the dominant harmonics will be absorbed by these two branches, that is third and fifth. So for all the three phases, we have this arrangement. We have three branches of this every phase, and these are designed to eliminate the third, that is provide low impedance path to the third, fifth, and higher order harmonics. Now, why the third, fifth, and higher order harmonics may appear in the line? This is because the loads may draw non-linear currents, as you have already seen. The nature of loads that you have may draw non-linear current. But see, actually, we have a single phase, three branch shunt. So for this problem, we have only a single phase, right? So we can draw like a single phase diagram, and we have the loads connected, single phase loads only. And here you provide the shunt, that is element. Okay. So this is the passive power filter arrangement where you have these are three branch, that is a single phase, three branch filter. So three branch means like this, as I have already told you. The first branch comes for the third, then fifth, and then high pass filter arrangement. This is the high pass filter arrangement. And these are connected to the line like this. This is A. So hope this configuration is clear how we are doing this, and what will happen, the load will draw nonlinear currents. This will be these harmonic currents, that is sinusoidal plus some harmonics will be drawn by the loads, and these harmonics will be appearing because of the low impedance nature provided by the shunt path of this passive power filter. These harmonics will be absorbed in this passive power filter such that the supply side we get sinusoidal currents. Moreover, the capacitors are also designed to provide reactive power support. So you see displacement factor to unity. That what means it's that the reactive burden of the load is also compensated by the capacitors. Like loads will demand reactive power, and the capacitors of these passive power filters are designed in such a way that at power frequency, the capacity, obviously the inductors and all those things will not dominate at the power frequency. The capacitance will dominate, and that power frequency, that means at frequency equal to 50 hertz, the capacitors will provide the necessary reactive power required by the loads, such that your displacement power factor is close to 1. That means that all the reactive power demand by the load is more or less cleared by the passive power filters. That is this filter arrangement. Okay. Because you must understand that all those L's, that is reactors, will not participate in the, I can say, harmonic compensation in the fundamental frequency perspective. Because at fundamental frequency, the impedance provided by the reactors will be very low and they will not participate. Okay, only the capacitors will dominate. So you must understand that their role only becomes significant if your signal that you are trying to filter out is having higher order harmonics. Then the inductors will behave to provide a low impedance path to those only those harmonics, those higher order harmonics. So this you need to calculate individually for the third, fifth, and high pass filter branch, the individual values of the inductors and capacitors. So in order to do such problem, you need to first calculate the reactive power burden. Once you know the reactive power demand, then you can calculate the value of the capacitors. And we assume that the capacitors are same for all the branches, that the third harmonic, fifth, and higher order high pass filter branch. And after we determine the value of capacitors, that is, we assume C3 equal to C5 equal to CH. And once capacitance is known, we know that for each branch to provide low impedance path to that particular harmonic, we need to do the resonance criteria, because obviously the high current will be limited by the R, the resistance. And to calculate the resonance criteria, we just apply omega 3 equal to 1 by root L3 C3, omega 5 equal to 1 by root L5 C5, like this. Okay, omega n equal to 1 by root Ln Cn, when Cn is known, omega n is known. For that harmonic, you want to provide the low impedance path. So accordingly, you can calculate Ln, that is nth harmonic rejecting reactor value. So for after finding the nth harmonic rejecting reactor value, you can also determine, since you know the quality factor, so XL by R, XLN by Rn for quality factor for the nth filter, nth harmonic, I can say. So that way you can calculate all the values. So this is the basic approach how we do for these kind of problems. So first let us calculate the reactive power burden. Okay. So what is the type of load you see? Load is thyristor bridge converter, 45-degree firing angle, and you assume that the load is of a single phase nature, thyristor bridge converter with a constant current, like this, as we already know. So this is the type of load that is connected. And you have a more or less constant DC load, which is having value of, I can say, 20 amperes. And you have the AC mains. This is the point at which you are applying the voltage from the line, maybe like this. And you provide some sort of passive filtering arrangements. So here is your passive filter, which is sitting, having 3 branches sitting within it. You have the third, you have the fifth, and you have the HPF. So these are all connected at this point, and then they are already connected to the neutral or to the return path, like this. So this wire is not there. This wire is the third wire, right? So this wire is actually connected to the neutral, like this. And these are all connected to the line, like this. So this is the arrangement. So the harmonics, obviously, you know, single phase thyristor bridge converter with 20 ampere DC will draw pulsating current, square wave current. You know already this. So alpha to 180 plus alpha, those currents will be drawn because you are triggering at alpha, where alpha is 45 degree and this is 180 degree. And this type of square wave you will see at the input side. This is the IL at the AC side of peak plus 20 and minus 20, right? So what is the, I can say, fundamental IL1 for square wave? Anyone remembers what is the fundamental RMS? So it is 4 into peak by pi. I can say IDC by pi. This is the peak into 1 by root 2 is the RMS. So 2 root 2 by pi into IDC. IDC is 20, so 2 root 2 by pi into 20. This is the RMS. Now, once you know the RMS value, you can calculate the reactive power. Obviously, reactive power will or active power will always happen for the same frequency currents and voltages, right? Other frequency currents and voltages, if V3 and I1 will not participate in contributing to any reactive power. So reactive power, because voltage does not have any harmonics, only the reactive power will or active power will be contributed by the fundamental of the current. So what is the fundamental reactive power that you can expect is V1 into IL1 into sine alpha, because alpha is the displacement, cos alpha is the displacement power factor, and the shift between the voltage and current fundamental is alpha. So sine alpha is the reactive power. So what you expect from this is 220 into, oh, what is this? Can you kindly calculate? 2 root 2 by pi into 20.
18 ampere.
Yes, 18 amperes. So 18 amperes is the fundamental RMS amp value. And so you multiply 18 times sine. How much is the angle? 45 degrees, right? So what is the var coming? (220 times 18 into 1 by root 2). So it is 2800 volt ampere reactive. So why I am calculating reactive power? I need the value of the capacitor. So as you know, the capacitor value will be capacitor value. What you know is reactive power. Obviously, this is the reactive power. You will get the reactive power by this method. First step is this. So step 1 I can write. Then step 2, calculate capacitor value. So what do you think? 3 branches are there, right? So every branch capacitor will contribute some amount of reactive power in the power frequency. So 3 branches are there. So 3 capacitors are having same value. As I told you, this is an assumption, but all the 3 capacitors will have to contribute to the reactive power to make it this. So 1/3 of the reactive power will be borne by one branch capacitor, of all which are equal value. So Q by 3 will be borne by one branch. But I need the value of capacitor of per branch, right? Inside this phase, as you can understand, as I have drawn, there are 3 such branches. In all branch, capacitors are sitting. Some capacitors of equal value. All those capacitors will be contributing some amount of reactive power at power frequency. So I want all the 3 capacitors to contribute equal amount of reactive power such that they sum up to be this. Such that if they can contribute that much of reactive power, our supply side will not be burdened with some reactive power and we can have unity power factor. Because anyways, I am doing harmonic compensation also along with reactive power compensation. So my distortion factor will also be good. That is, distortion factor will also be low and displacement power factor will also be high, such that you can get, distortion factor and all displacement power factor will be close to 1, such that you get unity power factor. So I don't want any distortion, as well as power factor should be close to unity. So Q by 3 divided by your reactive power. So V square by XC is the capacitance value, is the reactive power value. And reactive power, what is XC? XC is 1 by omega C. So V square into omega C is Q. So C is Q by V square into omega, right? Now what is the capacitor value for per branch? Per branch is bearing 1/3 of the reactive power. So C per branch is Q by 3. because that is the reactive power which they will contribute, divided by V square into omega, right? So V RMS obviously. So what is it coming? Calculate. So C per branch is coming as Q by 3 VRMS square omega. Calculate. 2800 by 3 omega is 2 pi into 50 into VRMS is 220 square. What is coming? (61.4 microfarad). And as I told you, C3 equal to C5 for the third branch, fifth branch, and HPF all are same. So this is an assumption. Now with this, we know the quality factors. So individually you can determine, right? The value of R's. First determine the value of L. So L3 is, I told you, 1 by root omega 3 C3. L3 you tell me. L5 is 1 by root omega 5 C5. Let me charge again. And obviously LHPF. In similar way. You calculate and tell me. What will be the value?
Sir, omega 3 is 2 pi into 50?
No. Omega 3 means third harmonic omega. So it is 3 times omega.
Okay.
Omega 1. And omega 5 is 5 times omega 1. Fifth harmonic angular frequency, right? And LHPF 1 by root omega, I can tell HPF into CHPF, as you can understand. So just tell me L values for the 3, I can tell sub branches like that inside this passive power filter arrangement. Else you tell me, okay? In millihenries you can tell. So omega 3 means 3 times 2 pi into 50. Omega 5 means 5 into 2 pi into 50. And omega HPF you can tell for the 7th onwards, okay? Because I don't have space, I can erase this portion. Remember the capacitance value, I am erasing this one. Tell me now.
4.157.
Yes, 1 second. Just let me erase.
4.157. Henry.
Which one? L3.
L3.
You just plug in 1 second. C3 equal to C5 equal to CHPF, which is nothing but C7 equal to 61.4 microfarad. You put it in here. What is coming? Let me also check. 1 divide square root.
Sir, L3 is 4.157, Henry.
Yes, just let me once calculate. Yes, what you are getting? .4.157
L3.
Henry or millihenry?
Henry.
Okay. and L5 and you calculate LHPF. Sorry, 1 second. Just let me do one thing, that here omega is 1 by root LC, okay? But your L value, if you calculate from the resonance criteria, it will be 1 by omega square into C3, okay? Just check. Omega, we want the resonance criteria, so it will be 1 by root ln Cn. So omega square will be 1 by ln Cn. And what will be the value of Nn? Ln omega square Cn. So please update, this is the formula, right? Because resonance criteria happens when your frequency matches as 1 by ln Cn. Now we design L and C such that our resonance frequency is at the nth harmonic. We want to provide resonance, means low impedance path to the nth harmonic. Now we want omega to be 1 by ln Cn. So omega square is 1 by ln Cn. Then ln is 1 by omega square Cn. So you apply this. We had written that formula incorrectly. Okay, you calculate from this and then you apply. So L3, you tell me L3, L5 and HPF means 7 onwards. Okay, what's possible scenario you take? You take the maximum possible inductance value. Okay. So this will
is 18.35 millihenry.
Yes, correct. And then L5. One by 5 into 314 whole square. Right, omega square it is. And multiplied by your that Cn. 61.4 into 10 to the power minus 6. So it is Julian. And if I plug in 7 here.
Here we have to multiply by 3, na sir, for finding L3.
3. Yes.
In this formula, Ln is equal to 1 by
omega square into Cn. Omega means no. I am writing generic. Okay, omega n square. So omega n is n times omega. Now you plug in omega 3 is 3 times omega whole.
Okay.
Now I will show you that when I calculate for the 7, what I am doing, L7 or LHPF is nothing but 1 by 7 into 314. Okay, for the 7th harmonic onwards. Now why 7? Because for 7th harmonic, your inductor value is maximum. We take the worst possible, maximum possible inductance value, such that all the harmonics are beyond that are already attenuated. So Cn is 61.4 micro. Okay, this is micro. So what is coming? L7, LHPF I can tell. So 3.3, right?
Yes, sir. 3.37
million. Now once you have the capacitor and inductor values I already gave you, and inductor value I have already determined, right? So now what you want? You want to determine the R. R3.
Sir, L3 is 17.29.
Okay, around 18. You must be doing some approximation. Okay. Don't approximate too much because the ranges are small, as you know, na. You apply omega as 2 pi into 50 only. Into 3.
And it is in Henry, na, sir, not millihenry.
Millihenry.
Okay.
You calculate, okay. 1 by omega 3 square into C3. Is it? Plug in the values, you will get it. Okay. I have calculated now, I am getting it. So if you, now I am rubbing this portion, okay. Now you want what? The R values, right? So R values, obviously, why you plug in R? Because to limit the current at the resonance. Otherwise, you will have zero impedance. At zero impedance for very small voltage, harmonic voltages, you will have surge in current. Okay. So instead of limiting the currents, it will limit the current by providing low impedance path, but the current drawn from the supply will be very high at the resonance condition. So we use some current limiting damping resistors. So these are all damped filters, right? So to calculate, the best way is you must know the quality factor. So single tuned ones, that is third and fifth, the quality factor 1 second. This the quality factor is given as 20. For the single tuned means one frequency, that is third and fifth. And your quality factor is 2 for HPF. That is means 7th and beyond. So you know quality factor means XL by R. So R is XL by Q. So if you want R3, you need to do XL3 by quality factor of third. Similarly, R5, XL5 by Q5. And RHPF is obviously XLH by R. H, I can tell. So calculate these 3 R values. Please note for 3 and 5 quality factor is 20, and for high pass filter the quality factor is 2. This Q, okay. So XLH you know, right? All the L values you know. What is XL? It is omega times L. So omega is 7 times omega 1. This is what? 7 omega 1 into L. Then XL3 means 3 omega 1 into L3. This is LH. And this is 5 omega 1 into L5. Okay. Calculate what is coming. So best possible, I can just remove all this. So what I am telling, XL3 by Q3 is your R3. XL5 by Q5 is R5. XLH by QH, because as per definition of quality factor, it is XL by R. Okay. Now calculate what is the coming these values.
0.864 for R3.
Correct. Now how you
R5 is
calculate?
0.8.
Yes. Yes, Q3 you take as 20, Q5 you take as 20, QH you take as 2, and for XLH, what you do 7 times omega 1 times LH. For this you do 5 times omega 1 times L5 and 3 times omega 1 times L3. L3, L5 and LH values already we have calculated. L3, L5, LH values I will give 3.3 millihenry, 6.6 millihenry, and L3 value is 18.3 millihenry. So using these values, if you plug these values in, and here, so R3 is okay. What is R5?
0.518.
Correct. And what is RH?
3.7.
Correct. I have the answers with me, so it is correct. Okay, so this is easy. Okay, this is one variant that is very common to determine the parameter values of the passive power filters. Okay, so another variant I can show you from passive power filter is this problem with the source inductance. Okay, so these are three-phase system, and you have some impedance. And after that, you have the filter. What is the THD of the AC supply current that you want to calculate? So this is obviously grounded, and this is also grounded, right? So first, let us determine the load. What is the, and obviously this is a three-phase system, but you have a 12 pulse thyristor bridge converter with 200 ampere constant DC current. So the load, if you draw the side, load side, so this is the supply side. Okay. So after the supply, you have a star delta configuration. So this is the 3 wire of the supply that is coming. You have isolation here and star delta configuration you have. And this is feeding thyristor based converter. Okay. So here you have a thyristor based converter. And here you have a thyristor based bridge. And this is connected in series. And you have constant drawing constant current. It is given, right? Constant DC current. So this is, you can model like a constant load. This is the configuration. So this is the supply side, right? Now you have connected star delta. So remember, star delta, there is a phase shift of 30 degrees for the line to line voltages, right? Because phase to phase voltage will have no phase shift because all are coming from the transformer, and phase to phase voltage conversion happens of the transformer. So there are no phase shift. But line to line voltage, which is fed to the converter based load, this line to line voltage, right? They will have phase shift of the star, because you know phase voltage and line voltage has phase shift of 30 degree. So this voltage is 0 degree. So this voltage would be 0 degree, but this line to line would have phase shift of the 30 degree, as you can also see from here. This is circumcenter, and if you assume this is star and the line of the star and delta, so this is, as you can see, this is 30 degree. Okay, so there is a phase shift of 30 degree between the star and the delta. So if someone asks you what is the IS1 and RMS and what is IS RMS, how will you determine for such configuration? So fundamental RMS, the technique is to use power balance, because power transfer happens only because of the fundamental current and then voltage, fundamental BP. So same frequency as I already told you. But if someone asks you to calculate the RMS value of the supply current, then you need to know the RMS value of the load current from the AC side and then reflect it to the supply side. So I hope you understood the problem. Now let us dive into it. Okay. So can anyone tell me how to do? So let's first draw the nature. How is the nature of the waveform? Anyone can tell me? For a thyristor based converter, controlled rectifier feeding constant current DC loads, that is highly inductive loads, RL loads. So how will be the nature of the current? Of the AC side. What is the shape? Remember, this is 3 phase, okay? So this is quasi square, right? The nature will be quasi square. So if you want to find what is the, I can tell, current at the AC side, because DC current you know, and AC side current will be quasi square, right? Quasi square waveform. Yes. So what is the RMS value? So you can, any one of you can tell me. For 3 phase thyristor based converter feeding constant DC currents. What
Square
is
root
the
of 2 by 3 IDC.
yes. So this is very important, right? And if you translate this is the RMS value, right? Or average value or peak value. What is it? This is RMS value, right? So this current RMS value you calculated. Please see carefully, okay? This you have with you, right? So similarly, this also you have with you. Agreed or not? So if I want to translate both these currents to this line, because I am concerned with the supply side. So I have one current. As you can see, this current is flowing through the phases also. And transformer action will be done on a 1-to-1 turns ratio basis. So first current, I will apply Kirchhoff's current rule. Okay. So first current is root 2 by 3 I
Yes.
angle 0.
Huh?
Then current will be 30 degree. So
आठ
root
वाजता
2,
है का?
yes, someone is talking, I think. So you sum them. What you are getting? You tell me. Hello. Yes, someone of you just use a scientific calculator. You can take this common IDC and then you sum up one angle 0 plus one angle minus 30 degree. What it is coming? I am using a scientific calculator. Tell me.
So IDC is 1, sir?
No. What I told you to take common root 2
Okay,
by
okay.
3
Okay.
IDC and you add
Okay.
one angle 0 plus one angle minus 30. What is coming? Yes, none of you have scientific calculator with you. Just see. Because in the exam also you need to do. If I write, then it will not be helpful. So one angle 0 plus one angle minus 30 degree. So it is coming as 1.93 times root 2 by 3 into IDC. So you are getting 1.57 IDC. This is the RMS value of the supply current. So none of you did this calculation from here to here. This is very important. That star delta phase shift you incorporate and then add. Yes, hello. Are you guys doing?
320. Yes, yes.
Yes, sir. Yes, sir.
So,
320 ampere.
no, don't forget about the answer. See the concept, okay? Because in the exam, you have to understand the concept and then attend. So what I did, you understand, right? I first, with the knowledge of the quasi-square waveform, I know the RMS value. I know this RMS value. I know this RMS value, but I should also consider take into account the phase shift, because you need to understand that transformation happens phase to phase. So this phase, and this phase will all be co-phasor. They will not have any phase displacement. But you know, in the line to line, they have phase displacement. So this current will have phase displacement with this current. So that was the main catch, that 30-degree catch. Okay, that from phase to line you go, and then line to phase you come. You have 30-degree mismatch. Okay. So 1.57, remember, okay. This is the RMS value of the supply in terms of this. So I translated this to this and this to the supply. So if this is IDC, then your supplies, and you are having a 12 pulse configuration with star delta configuration transformers, then you will have on this side what? 1.57 times IDC. So now I got IS RMS. So what is IS1 RMS? Let us apply the power balance. So up to this you understood, right? So now you see you have the thyristors, right? And then you have a cascaded configuration. So this power balance will do, right, from the supply and then to the load. So this voltage, you know, this is VDC, this is VDC. So this is 2 times VDC. This is V out, okay. And VDC is 3√3. I want to find the average, okay, V not average. So 3√3 Vm by pi cos alpha. Agreed or not? Yes, hello, nobody is doing, I think. You are doing with me?
Yes, sir.
So
We are
actually
doing.
formula, it is a 3√2√3.
Yes, I am telling. So 3√3 Vm by pi means this is average DC link out or output voltage, okay, for 3-phase thyristor based controlled converter. So this is average output DC link voltage, okay. And what is Vm? Vm is phase peak. Phase peak means phase voltage peak. So now I do power balance. What is power balance? Input side active power equal to output side power. So output side power is DC. So what is output power? It is V naught into IDC. V naught I already gave you expression. And input side is 3 times V phase into I phase. Obviously for the fundamentals, because power transfer, I am repeating, happens only for the fundamental. Because voltage does not have any harmonics. So current fundamental in line with the voltage will be responsible for active power transfer. Okay. So now I can write it as VRMS1, obviously phase 1, and IRMS phase 1 equal to 2 into 3√3 Vm cos alpha by pi. Three and 3. So this 3 and 3 will get cancelled. And what is Vm? Vm is √2 VRMS phase. fundamental. So VRMS phase fundamental will blow away with this. So what is IRMS fundamental of supply? It is 2√6 by pi cos alpha times IDC. Up to this is clear, right? So I have IRMS of supply as 1.57 IDC, which I showed you previously in the previous slide, and IRMS supply fundamental as 2√6 by pi cos alpha into IDC for a 12 pulse configuration. So this holds for a 12 pulse configuration. While doing the power balance, am I audible? Hello.
Yes, sir.
One small correction is there. See, while you do the power balance, 3 times VRMS phase fundamental into IRMS phase fundamental, you are doing the power balance, right? So there should be one cos alpha term because active power balance we are doing, right? The displacement power factor we should account for. And this side we need to do 2 times 3√3 Vn means √2 times VRMS phase 1 divided by pi into cos alpha into IDC. So this was V not average, this full term. So this cos alpha and this cos alpha will go away. I think the screen is lagging. And then this VRMS and VRMS will go away. I think I need to change my network. This is okay. Screen is now visible, right? Yes, is it visible screen?
Yes, sir.
Yes, sir.
Yes, yes.
Yes. So now you see we are doing active power balance, right? To determine the fundamental RMS. Because I told you that only the fundamental is responsible for active power transfer in line with the voltage. Not only fundamental, V3, I3 will contribute to some active power. V1, I1 will contribute to some active power, but V1, I3 will not contribute. Similarly, V3, I1 will not contribute. Like that. In-phase currents and voltages contribute for, obviously with same frequency. In-phase voltage and current with same frequency contribute for active power transfer. If you do the integration, you will understand. Other terms will go to 0. Okay, so now you see this is going out. So now you see this 3 and 3 also going out. So IRMS phase 1 or phase fundamental is nothing but 2√6 by pi into IDC. So no cos alpha. Understood? Please note it down. Okay. So now you have the two formulas. Up to this is done, right? So this is IDC. So now you calculate IRMS and IRMS 1. What is it? 1.57 IDC or 1.577 for more accuracy. And IRMS 1 is 2√6 by pi into IDC. Do this two and tell me. Obviously, you understand remaining will go to the filter. So IRMS square minus IRMS 1 square whole root over is the harmonics. So filter rating. This decides the filter rating. So calculate. Tell me the filter rating also. First calculate these two and then calculate this.
$312. IRMS 1.
IRMS 1, 312, correct? And IRMS?
IRMS is 315.
Okay, so if you do accurately, you will get 315.4 and 311.8. I have the answers. Okay. So what I harmonics? I harmonics RMS of load. So complete will not be absorbed by the filter. So first let us calculate. So as you understand, fundamental and actual load RMS. If you subtract, you will get the harmonics, right? So this is I RMS square considering the harmonics. All the harmonics are appearing at the supply. And these are only the fundamental. Remaining are the harmonics. So I harmonics RMS of supply. So 315.4 square minus 311.8 square whole root over. What is it coming? .52 amps.
Yes, sir. 47.5.
Now understand that this is the harmonic content have appeared at the supply side. If you have not provided any passive filter arrangement, but your passive filter is doing what? It is also providing some impedance, which is actually mitigating some portion of this harmonics current, but not completely. So if you see, let me draw the single phase equivalent line diagram. So if you see the low source impedance, it is what? It is only a reactance, right? It is given somewhere. 5% source impedance, okay? So source impedance if I want to draw, and after that I have this filter. So this is single line diagram, okay, that I'm drawing. This has some own impedance. This is also the return path. After this you have the load. And this is also the return. So now I know that load will draw harmonic currents, right? This is transferred to supply side, okay? Because whatever I am calculating, I am reflecting it to the supply side, as you may understand. So this is I can write source fundamental plus I source harmonics. So I source harmonics I calculated. I source fundamental also. And together I have ISRMS, which I have already shown here. So obviously this is the phasor summation. So now this will partially, out of this, it will partially draw some harmonics, and some harmonics will appear here. Remaining will be responsible for the supply current, because supply current will anyway be distorted, because this is only providing compensation for the 11th harmonic through its impedance, which you already know, I think. So you have to calculate. So after you know this impedance, right, you can calculate what is the current that is coming here. Agreed or not? So first calculate the impedance of this branch, right? So I think I have one more page. No. So just remember these 2 points, right? I will just write it in a corner. IRMS is 1.57. You can write the answer also. 315.4 and IRMS 1 is 311.8. So calculate what is the value of capacitance, because this branch is also providing reactive power compensation, right? If you read the problem, yes, improve the displacement factor to unity. So the term, when they tell displacement factor to unity, they mean inherently that reactive power compensation, because no phase shift. What is displacement factor? Displacement factor is the cos of the angle between the fundamental of the voltage and current. So there should not be any phase shift, means reactive power compensation is already provided. So for that you need to calculate capacitor value on a per phase basis. So as I told you, this will be Q1 divided by 3 Vs square omega. So what is Q1? Q1 is the reactive power. So this is 3 times Vs phase, Is phase, cos alpha, divided by 3 times Vs, obviously this is per phase square into omega. So 3 will go out, and V phase, what is reactive power? Let us calculate. Sorry, this is sin alpha, right? Let's calculate reactive power. Okay, this is Q. What is reactive power? Calculate, because Is phase fundamental, you know, right? This is Is phase fundamental, because this is star connected. Assume, because it is nothing specified, so the supply side will assume as star connected. So what is Q1? It is 3 times. What is the line voltage? 415 divided by root 3. Do times V phase into I phase, or you do root 3 times V line I line. So V phase into I phase. Okay. So this is V phase. I phase and I line are same for star. So this is 311.8 into sin alpha. Alpha is 45 degrees. So what is Q1 coming? So why Q1? Because we want to find capacitor value. Actually, we need the impedances. So root 3 times 415 times 311.8 times sin alpha. Or alpha is 45 degrees, so 1 by root 2. So 158.5 kilovolt. Yeah. So what is it? 158.518 into 10 to the power 3 is the net reactive power Q divided by 3 times V phase square. So V phase is 415 by root 3 whole square into omega. Omega is 2 pi into Q. So what is C value? You tell me in microfarad. 2929.7 microfarads. So obviously CH and C will be same, because you are using a high pass filter also. So this high pass filter is tuned for the 11th order and higher, like that it meant. So when someone tells you nth order high pass filter arrangement, then it is a single sublayer only, but the threshold they are giving you, that greater than or equal to, high pass means higher than or equal to the, so the one only. So that's why you don't need to divide C by 2 or 3, because if it was another layer providing 11th and then 5th and then another high pass filter layer, then all those capacitors would have participated, just like the previous problem. We divided actually by 3, because per phase we have 3 layers which are contributing to the reactive power, because capacitors we are assuming same value, but here only one single layer. So capacitance value per phase we determine by 3, but no more by 3, because in per phase we are having only one capacitor sitting there. So that is the absolute value of the capacitor. So this is the arrangement. So the language is important. So it is telling that 11th order high pass damped filter means that for one only it is greater than or equal to 11. It is providing the high pass filter nature. Okay. So what is LH? This CH, okay. So this CH, this LH, this RH. So LH is 1 by omega square into CH. What is it? Calculate. So 0.029 millihenry is coming. And RH is XH by QH. Now XH means you are having omega. So that 11 times 2 pi into 50 into L. Omega L, okay. Now 11 divided by quality. Quality factor is 2. Just check what it is coming RH value.
Point 0.05.
Yes, correct.
Sir, एक doubt है.
बोलिए.
Sir, with this method of calculation for C, we will always get same C for every frequency. Every
Correct.
filter.
Correct.
Why is it so?
No, please be sure you are getting same C, not same XC. The reactance will be different, right? Please understand this. This is very important.
Correct.
Same value of C, but when you are at the power frequency level, that is at small omega, the capacitor will only dominate. Please understand, this is very important. When you are at the power level, that is 50 Hertz, this inductor impedance will be very low. So it will behave like a wire. So what is happening that at power frequency level, you are only connecting a capacitor, which is providing reactive power compensation. But whenever your frequency, if you draw the Bode plot of this kind of filters, this will come like this, that high pass filter. That low frequency impedance is low, higher frequency impedance will go up. Sorry, higher frequency impedance will go low. Impedance will go low and its acceptance of harmonics will increase because it is providing low impedance path to the higher order harmonics. These together.
That means, sir, for any frequency, the method for calculation of C remains same.
Because we are assuming the capacitance is providing reactive power support at the power level. Its primary role. Whenever you are going on the higher frequency side, that this inductor role will start dominating. That's why we are putting in the resonance condition, right? 1 by omega square, what that this condition. Any one you fix. And other one you have
how do we choose between high pass and single tune?
No, single tuned is different. Single tuned is for one frequency, okay? In a branch, you are wanting to provide that is selective harmonic elimination, that is selectively the dominant 11th harmonics, you want to provide a special dedicated branch for the 11th. Then what you will do, just like the previous problem, you need to provide a dedicated branch. But high pass filter is cheaper because you are designing for greater than equal to 11th when you know that your load currents don't have such harmonics. Why you want to design for third? When you know that your system will not bear third harmonics for a 3-phase 3-wire, why you want to provide a single branch, sub branch I can tell, like we saw in the previous problem for the third. I will put for 11th or more because I know load currents will not bear those harmonics, and I may simply provide HPL like this.
Then when we target a single particular frequency, then we go for single tune.
But please understand that is for very highly distorted load currents. If there is some dominant, too much dominant 11th harmonic, then you need to provide, because this high pass filter does not provide selective harmonic elimination. If you design for selective harmonic elimination,
is low.
Yes, impedance is low, but not too low. For single tuned, they are very low. That they are designed for that particular harmonics only. That resonance criteria will happen limited by the R. So that is a trade-off that we need to do depending on the nature of the load connecting to the system. Obviously, we are doing numericals, but In the practical situations, we do some analysis on what kind of load current harmonics it can bear, and what we want to attenuate from the supply. Also, you know that when we go to the much higher order harmonics, then their amplitude also reduces. So maybe a high pass will only do. But if it is too distorted and you want to provide the harmonic compensation, like to provide by providing a low impedance path, then it is okay to provide a dedicated single tuned arrangement in a sub branch, like we calculated for the previous problem. But in this problem, we are only giving
in general, single tune filters are for lower harmonics, like 3 and 5.
Not necessary. They may be for higher order, and I may also blow it up to 13th order HPS. Depends on the application. If you need specific attenuation of some harmonic component, it is better to go for single tune. And it is optional that you can keep a HPF, because to mitigate the switching ripples, if you have some converter based loads, they will be switching. So too much higher switching ripples may also come at the supply. So HPF may do good there, because it will suck all the higher order harmonic ripples, as you see from the board plot. So all the bands it is providing attenuation, right?
Okay.
It will pass all the bands. That is, it will attenuate all the bands from the supply. So like that. So you calculate the value, assuming CH to be to this, and LH you calculated. So RH you calculate 0.05 you calculate locally. So now what I will do, up to this you please note down, okay, the value. I am rubbing this portion. So we have RH value as 0.05 ohms, LH value as 0.029 millihenry, and C value as, or CH value as 2929.7 microfarad. So I told you the harmonic, what was ILH or ISH, the reflected harmonic, that is IS square minus IS1 square. It was coming as 40, I think 6 point something.
Sir, we have found one. Excuse me, sir.
Tell me.
Sir, we have found the RMS value of the current. So that is without filter, sir?
No. RMS value of the supply current without filters is the RMS value of the supply side current minus the RMS fundamental value of the current. Will give you the harmonics RMS value. That is why I am writing ISH.
Okay.
Because without filters, obviously we are calculating, because we want to know how much current to flow where. Because filter impedance, you know, na? This is the filter impedance. Because
Yes,
filter LUs, you know. Only because you have the effect of the source impedance, your things will start deteriorating. Just see how it will be like this in this condition. Okay. Now you know that 47 amperes of harmonics current is there. Now how much amplitude will go where will be decided by what? Even when you do the board plot analysis, what you do, you see the impedance, how much impedance it is giving to the harmonic component. So it is better that when you do that, please understand. Let me draw the diagram. So this is the nature of the. So there we are providing some filters, and here is the load. Now what is IS square minus IS1 square? It is reflected load harmonics, ILH. So the ILH plus IL fundamental. Now can anyone tell me? Now you understood this, that supply RMS minus supply fundamental RMS is the load harmonics. But can you tell me what will be the harmonics that will appear at the supply side? That is more concern. Supply harmonic. This is load harmonic. So this load harmonic reflected to supply side, because all things we are doing reflected to supply. The load DC side, we are translating it to the supply side. So load harmonics reflected to the supply side can be estimated from effective source RMS minus or supply RMS minus supply fundamental RMS. That will give you the load harmonics reflected to the supply side. That I am writing as 47 amperes. Always it gives you like this. Now you want to, because there is an impedance sitting here, which is termed as the source impedance, and as well as the impedance of the supply or the filter for the load. Hope you can imagine what I am telling. So reflected harmonics at the supply side I need to calculate. So what I will use here? At this point, the current, this ILH, will divide among the two impedances. So if you want to find out the Thevenin equivalent, just sort this and you will find these two are coming in parallel. Agreed or not? This ZS and ZPS or power filter. These two are coming in parallel. I think my screen is again lagging. Then I should turn off and then represent.
Slide is not visible, sir.
Yes. Just 1 second. Visible? So what I was telling, load harmonics reflected to the supply side, you know, because IS fundamental, you know, you want that minus IS net RMS, which is actually the load harmonics reflected to the supply side, total RMS divided by fundamental RMS. Just think like that. Load current harmonics reflected to supply side all over RMS minus fundamental RMS will give you effective load harmonics reflected to supply side. But I want how that harmonics is splitting among my filter and the supply side, because filter will absorb some portion of that harmonic current. So this harmonic current ILH, can you see? Just let me know. This ILH reflected to the supply side will split among this filter and this source, because both the Thevenin equivalent is coming in parallel. Yes, agreed or not? Hello.
Yes, sir. Yes, sir.
So if you want to see the Thevenin equivalent from this node, this current will see two paths. This ILH not completely will be absorbed by the filter. That is my main point that I want to keep. All we did was reflected the load harmonic content current totally to the supply side, which I denote by ILS, for example. Supply reflected load harmonic. Now, what I did, this supply reflected load harmonics had two components, one fundamental and another harmonic. So ILS was built of two terms, ILH and IL fundamental. IL fundamental is what I am denoting by IS1. This actually should be IL1. Because still we don't know what is the fundamental of the supply. And this ILH, ILS I can tell. The denotions are very important, okay? ILS. So load current reflected to the supply side containing harmonic and fundamental component minus the fundamental component will give you the harmonic content. This is the ILH, which is the harmonics current. Because harmonics current only we need to split to determine the harmonic content at the supply side. So what is the supply harmonic? Can anyone tell me? If I know the harmonic content at this side, and I know by Thevenin from this point it is splitting into two parallel paths. What is the supply side harmonic content? 47 times this ZPF power filter inverse. Current division happens in the inverse law. So if I want to find out the source side current, then I do the inverse. Agreed or not? Agreed or not? These are the supply side reflected harmonic components. So ISH. And supply will also be at the fundamental of the load. So I supply will be ISH harmonics plus IS1. What will be IS1? IS1 will be equal to IL1 because supply will throw the reactive power of the load or reactive component of the load, fundamental plus ISH. So tell me what is ISH? ZPF is nothing but what? You can calculate from this. LH, R and CH you know. Just calculate what is the impedance. RH you know, right? And what is XSH? Here, from here. So I need ZPF. ZPF is nothing but the impedance provided by this. And just remember this is for 11. Okay. So you calculate for 11. Tell me the impedance of this filter. So you can do what? You can do R plus J or R times J omega L divided by R plus J omega L plus minus J by omega C, because these two are in series. So equivalently you can determine the impedance of the power filter. So impedance of power filter, once you know the ZS, which is J times, what is it given in the problem? ZS is given, right? So it is per unit, right? 0.05 per unit into per phase unit to do. So let me just clear the screen, otherwise it will be too difficult. So hope this is clear that what we did. I'm just explaining once again. So this is load reflected to supply side. This was drawing some harmonics component IL1 plus ILH equal to IL. These are phasors. This ILH will split among the filter, and because filter is more or less reactive, only small amount of resistance is there. So this ILH will split as per the inverse rule, and we have ISH and IS1. IS1 is equal to IL1, more or less. So this is the thing. So ISH we are trying to determine. So ISH is nothing but ILH, which is 47 times the inverse. Now we need both ZS and ZPS. Okay. Now what is ZS? It is 0.5 per unit, 0.05 per unit. So do you know how to go from per unit to your actual ohms? That is, what is the impedance in ohms? Can anyone determine? It is nothing. ZS is what? ZS per unit means actual impedance divided by base impedance, right? What is the base impedance? It is nothing but V phase by I phase. all in per phase, okay? Per unit always in per phase. And impedance in per phase also, you calculate. So 0.5, so per unit times Z base. What is Z base? V by I. So what is V per phase? 415 by root 3. What is I? IL RMS? 350. So calculate what is coming. Z is in ohm. Please calculate with me because this is important problem. Okay. So I am getting J.038. Everyone getting me? Yes or no? So ZS I determine. ZPF you determine. So power filter looks like this. You have L in series with RH, a parallel with RH, and then you have capacitor CH. So this impedance I need. So if I do and this is ISH I can tell. Then I am getting ZS as 0.J0.03 I think. Correct? Yes, 0.038. So can anyone tell me intuitively what it should be for the 11th harmonics? Intuitively. Anyone? What should be ZPF? Otherwise, this whole session will be of no meaning. Because if you can tell it, you have understood the meaning of the session. So what is the high pass filter doing? Can anyone tell me? It is attenuating 11th and providing slightly lower attenuation to beyond. But it is attenuating. That is providing low impedance path. Now can anyone tell me to which harmonic is it providing the least path, lowest attenuation path or lowest impedance? Can anyone tell me?
11th.
Correct. So for 11th, what is the condition? This L and C impedances will cancel out and provide a resonance-like phenomenon. So effectively, this will be nothing but RH. Agreed or not? This was what we designed L and C with, right? Throughout the session, what we did, how we determined L and C values. C we calculated for reactive power, and then we did omega equal to 1 by root LC. By this, we are telling that these two impedances will be cancelling each other by resonance phenomena. So inherently, for 11th, these two will cancel each other. The impedance effect of these two, that is R parallel with L and series with C, the effective impedance and the impedance of this shunt path, that is the LH, will cancel each other equivalently, and only R will be remaining. When you go through this path, you will cancel, and then it will go with R. So ZPF is RH for the 11th. So when you do with RH is 0.05 and Z PFU plugin and ZS is J0.038. And when you do all this, ISH will come out to be 5 amperes, right? 5.472. So IL harmonic, that is IS harmonics, ISH, that is supply deflected harmonics, RMS component, will come out 5.5 shunt division, okay, inverse law. And to find out the THD, what you do? What is the definition of THD? It is nothing but supply side harmonics divided by supply side. Can anyone tell me? What is the definition of THD? Harmonics by fundamental, right? RMS, all RMS. Now supply fundamental, I told you, is same as load fundamental. What is supply fundamental? It is this 311, right? C top right corner. So I have the supply harmonic RMS, reflected harmonics supply side RMS. So your THD will be 5.472 divided by 311.8. What is coming? 1.75% around. So this is the answer, right? So these two are big problems, but the intuition was that for that particular harmonics which we are providing attenuation, that loop will just be a resistive loop. The current for that will be limited by the small resistor. So that is the way we are doing the design of the L. So when we are calculating the impedance for that particular frequency, we will incorporate L and C. Just R will do. Okay. Hope this is clear. Any doubt in this? Any doubt, you can just let me know. Okay. Otherwise, I will move to the active filters. Put out. So I think we started at 6:30. I can take another 30 minutes. Up to 9 I can take, or
Sir, one doubt is there, sir.
yes.
Sir,
So
we have found a TSD. We have found a TSD of supply current that is without with passive filter, no, sir?
Correct. Because we only did why we did first determined without, because we wanted to find the harmonic of the
what
load.
the value for, sir, without passive filter?
With passive filter. With passive filter also some harmonics
sir,
will
then,
be reflected. Because of the source impedance.
So then what will be the value for without passive filter, sir?
Without passive filter, your full harmonics will be appearing. This ILH. Full harmonics will appear. Okay.
Yes, sir.
So the value without passive power filter will be nothing but ILH divided by IS1. So you calculate ILH is what? 47 divided by 311.8. So calculate 47 by 311.8. 15%. Okay. Clear or not?
Yes, sir.
Let's move on to the. I can take up to 9. If you don't have any problem, I will take up to 9.
Okay, sir.
Okay. Let me take some water and then So the active power filter, let us start, right? Let's start with a simple problem. That a single phase shunt active power filter is employed for harmonic current compensation for a single phase load, diode bridge rectifier based load, just like as you saw constant current, 45 ampere it is drawing. Now it is simply asking you to calculate calculate current rating of the AP to provide harmonic at unity power factor. So it is easy, right? So what you need to do, you know that ISRMS fundamental. You know, for a square wave, this will be a square wave, right? At the supply side, because it is constant DC current at the DC side. So at the AC side, it will be toggling between plus 45 and minus 45 for a single phase load, fully square wave, 180 degree. So what will be RMS fundamental? Supply side, 2 root 2 by pi into 45. Calculate what is coming. It is coming as 40.5 amps. 5.1. So ISRMS is square wave. What is RMS value of square wave? Same as this, 45. So ISRMS square minus ISRMS fundamental square is the harmonics. What is it? 45 square minus 40.51 square whole root over. What is it? (19.57 amps). Right? So who will absorb this harmonics? The filter. So current rating is without any source impedance. So all the harmonics will be directed towards the filter, right? So current rating is 19.57 amps. Understood? This is easy. So again, screen is lagging. I will just reshare. So understood? Just see and just share. So I hope this is clear, right? Hello?
Yes, sir.
So let's move to the next problem. So now see. So a shunt active power filter is used in parallel with single phase AC supply. It's a shunt active power filter and it maintains almost unity power factor. So the supply is feeding charge bridge rectifier, charging a battery 150 volt 20 ampere, okay, with a small resistance. Now volt ampere rating of the active power filter is being asked. So in this kind of problem, you must know that we are trying to maintain almost unity power factor with the active power filter. So for volt ampere rating of the active power filter, you need two things: the voltage and the current. So voltage, can anyone tell me what is the voltage rating of the filter? shunt filter.
220 volts.
Correct. So now all the thing we need to determine is the current that the filter needs to absorb. Okay. For that we need to actually determine the harmonics current. So for harmonic current we need fundamental of supply and RMS value of supply. Because then we'll try to determine the harmonics component by RMS minus fundamental. So you need IS RMS and IS fundamental for that this kind of loads, that is RE based load.
So your screen is lagging or it is blank now. Okay. Yeah,
Now
it's
it is
come.
correct.
Yeah.
So what I was telling is that both the currents we need to determine for fundamental RMS and your total RMS of the supply. Okay, that will help us determine the harmonics. So you must know that for this kind of loads, we are trying to maintain unity power factor. That is what we are trying to maintain. We are trying to maintain sinusoidal currents at the input side, and remaining harmonics will be just let us draw. Screen is not lagging now. So single line diagram I am drawing. So these are the loads. So this will draw I harmonics and this will go I harmonics plus IL and this will be IL1. There is fundamental of the load, the supply will power. Okay. So now what I'm trying to do, so just see the current directions, just it will make you confused. So I will again. So harmonics will be supplied by the filter. So this direction. Okay. Now apply KCL, you will get IL1 equal to IS1 and IL equal to IL1 plus ILH harmonics. So ILH will be supplied by this. Understood, right? So RE based load with diode rectifier, right? Okay. Small resistor and then your now this current is discontinuous in nature because the conduction can only happen in this period. Agreed or not? When your V sin omega t is greater than E, then only the power can flow in this direction to charge the battery. So for that we have actually, if this is alpha angle where the intersection is happening, where alpha is sine inverse V, where V is this amplitude by, because you can derive also V sine omega or V sine alpha is E, so E by alpha, so E by V will be there, E by V. Okay, E is the battery voltage and V is the amplitude of the sine. So this single phase, so this is 220 and peak, so 220 root 2. So alpha, if you determine, alpha will be sine inverse E by 220 root 2. So what is alpha coming? 28.8 degrees. Got? So now we can, I gave you the formulas for these RE based loads, right? From there we can find actually what is the value of, because one thing is given here. Okay? The battery charging current is given here, 20 amps. This is the I average. The AC side RMS current, okay, that is flowing into the DVR. This is the DVR, then you have the RE load, right? So this AC RMS current is what is given by this formula. So this is AC RMS. And what will help you to determine R is the DC average current, which is here. Please understand. So I DC average is simple, is given by this formula. 1 by pi into R, and you have 2 VSM cos alpha plus 2E alpha minus pi E. Is simple formula. So this will give you the value of R. So just try to determine what is R here. By putting IDC average as 20 ampere. Alpha you know as 28.8 degrees. This is 28.8 into pi by 180 in radians. And this is also pi into E. Then I will understand whether the formula is okay or not. Because IDC average you already know. You find out R. Take R here and bring this down. So R is nothing but 1 by 20 pi 2 times 220 root 2 cos of 28.8 degree plus 2 times 150, that is battery voltage into alpha. Alpha is pi by 180. That is 28.8 into pi by 180 minus pi into 150. Calculate what is R is coming. Yes, if you calculate this, you get 3.578 ohms. So this is the DC average expression, which is this current, which is discontinuous. And if you find the AC RMS, then you use this formula. So don't confuse, right? So please take it down and then I will move on. So R value you got, okay? And then similarly what I told you, power, output power is IDC square into R plus E into IDC. Simple. So this you calculate now.
So how much was your R value?
3.578.
Okay.
So what is IDC? 20 amperes. 20 square into R. 3.57 plus 150 into 20. It is around 4431, right?
Yes, sir. That was the same answer I got earlier also. I don't know then
Yes,
what.
but the formula I gave you, na?
Huh.
No, the formula that DCR, please know. And the DC average value will help you to find out the value of R, which you need in this problem. So that was the. You just please
Okay.
take these two formulas down. These are useful in multiple problems.
Okay. Okay.
Formula is correct because we determined the true value of R. So if you now know the active power, by power balance I can find out the fundamental of the supply. The net power is 4431 power divided by voltage, right? So voltage is what? 220, right? RMS. This is what? So I find IS for RMS. It is 4431 divided by 220. 1.4. Done? Sorry, 20.14. 20.14, okay? Or I will write 20.14 amps. So this is the supply fundamental that you are getting. And you also calculate what is the net RMS current, IES RMS. You use this formula. Because AC RMS current, net. Fundamental we did by power balance, but net AC RMS current you will use this formula. This formula. So if you calculate, you will get the answer. You just put R value as 3.578, this as VSM as 220 root 2, E as 150, and alpha value you plug in terms of radians, and then you will get this as around, you get 25 amps. So what is the harmonics current, RMS? Is 25 square minus 20.14 square, right? Whole root over. So harmonic current you actually get in 25 square minus 20 square, what is coming? 15 amps. Just check whether you are getting 25 amps, okay? Okay. So calculate what is the current volt ampere rating. It is 15 times 220, okay? So VA rating is 220 times 15. Just let me check the answer, if it is correct or not. So fundamental current is what you are getting, around 20 amps, right? And net current, okay, it is correct. Yes. You still just find this, what you are getting, you just calculate. Can anyone calculate?
Which one, sir? IES RMS?
IAC RMS. Just calculate and let me know. This is half, okay? Whole to the power half. Just be cautious. Just calculate, it will be good. Just try one problem. Yes, anyone did? Alpha you take in radians, okay? For this. Otherwise you take in angle inside this. Depends on what calculator you are using. So
I'm getting 26.7.
correct. So 26, around 26.7 you take. 26.7. It is better we do it actual values. 26 around I am getting also 26.7 amps. So your harmonics current will be 26.7 square minus 20.14 square. Just calculate 26.7 square minus 20.14 square whole root over.
17.55.
17.5, yes. And then 17.5 multiplied by 220 is the answer. Around 3.8 kVA. Okay.
Yes, sir.
So it is 26.7. Yes, correct. Everyone getting it? If you are not getting, kindly let me know. Because this formula is important. You need to do it because many problems maybe they are from RE based loads. And both the RMS and DC formulas you need to know. Only this formula you need to just remember. You may have also seen that for the past few weeks we are using it multiple times. Only this formula we are remembering. No other formula I gave you. All we are deriving. And after multiple times of deriving, you will remember it. Okay. Yes. So now just see the displacement factor is 0.88 for this kind of three-phase DVR based based load, drawing 0.88 displacement factor. So displacement factor is nothing but the cos of the angle between the fundamental of the voltage and current. So if is given as 0.88, I will drive it first. Just let me know if you have any. Okay, just let me plug in the adapter. Okay. So displacement power factor is 0.88 and crest factor is given as 2.2. And each specimens 85%. So can you tell me what is the fundamental active power? Because here you need to calculate what? RMS current rating of the filter for providing reactive power compensation. Okay. So first let us determine what is the active power to be transferred. So active power we are determining. And per phase basis we are trying to determine. Okay, first let us determine the active power. Okay, active power is already given, I think 21 kilowatts. Yes. So 21 kilowatts is the active power. From active power, what we can determine? We can determine the fundamental, as I already told you. So 21,000 divided by 3 into VS phase. So calculate what is the fundamental. $30.31. This is IS1. Now this IS1 is actually the active component. Please understand. It is not unity power factor. So don't confuse with just trying to determine the fundamental component with respect to the active power. So this is always fundamental component, but active component when you are trying to determine IS1 with respect to active power. So ISA is 30.31. Okay. But you need to determine IS1. IS1 is nothing but 30.31 divided by cos of alpha. Because IS1A, IS1 cos alpha. Cos alpha is nothing but the displacement power factor. So what is IS1? 30.31 divided by cos of alpha is 0.85. What is 30.7 divided by 0.? 35.66.
So how did you get 0.85?
0.88, sorry.
Yes. Yes, sir.
So this is IS1. IS1, why we try to determine? Because I want to determine the filter current, right? Or because what is to provide only reactive compensation. Now IS1 sine theta 1 from displacement power factor you can get is nothing but filter current, because filter is responsible for reactive compensation, right? So IF is what? IS1, actual IS1, this one, not active component. Actual IS1 is 34.44 times 1 minus displacement power factor square, because sine of theta, na, cos of theta is displacement power factor. So sine of theta is 1 minus displacement power factor square whole root over. So 1 minus 0.88 square, right? What is coming? Just see, 16.36 amps. So IF is filter rating current is 16.36 amps. So another type I just want to make you see. Okay, is for this one. So it is similar problem, but you need to maintain unity power factor and reduce the harmonics in the AC mains. So calculate the RMS voltage at the input of the diode bridge rectifier, and you are charging the battery with 264 volts, 12 ampere average current. Now, one thing that you need to understand is that you need to minimize the harmonics as well as ensure continuous conduction. Please understand the difference between one of the problems of RE based loads that we did and this problem. There we were allowing the discontinuous currents in the supply side, but here we are not allowing discontinuous currents. We are trying to make sinusoidal currents continuous currents to charge the battery. If the that is the input currents, that is the AC currents, are continuous and sinusoidal, then what will happen? Can anyone tell me? If input currents are not discontinuous, which should actually be for a RE based load, then what is happening is that the voltage, that is input voltage to voltage input, I can write to the diode bridge rectifier, or AC voltage input to the diode bridge rectifier will be square for sinusoidal continuous input AC currents, because you are not giving a moment for the supply current to be discontinuous. That means you are continuously pushing currents. So what will happen, that battery with a small r will behave like a voltage fed load, and it will toggle the voltage between at the every cycle, 180-degree conduction cycle. It will toggle the voltage, and the voltage will be square. So the current will be sinusoidal, but the voltage will be square wave for allowing continuous conduction of currents throughout the cycle. So knowing this, you need to calculate RMS voltage of the diode bridge at the input of the diode bridge rectifier, AC RMS voltage at the input of the diode rectifier, and also the obviously the RMS voltage rating of the APF. So APF active, it is series active filter, right? That is connected between the AC inductor and the DC bus capacitor. So The series active filter, I think you are aware of that. It sits between the supply like this and the loads are connected. This load is what we are talking about. This is a single line equivalent. Okay. It needs to inject the difference between the two voltages, the sinusoidal voltage and the square wave voltage. That is at the input of the DPR, AC input voltage. So if it injects the difference between the two, then we can maintain sinusoidal currents, right? So the voltage at the RMS voltage, can anyone tell me? So VP, this side is the DC voltage is 264 volts, as you can see here from the problem. So the voltage toggles between 264 and minus 264 by square wave, I can tell. Then what is the RMS? RMS is RMS V0 AC is 264 volts. So that is the main catch of this problem, nothing else. And RMS voltage rating of the active power filter. So RMS voltage at this side, you know, 264 volt. At this side, you know, you have 220 volts. Can anyone tell me what is the voltage rating that the series filter needs to inject? It is 220 root 2 sine theta minus 264 whole square d theta, because we are trying to determine RMS voltage. So difference between the two it will inject throughout the cycle, and we need to take the RMS. So square then mean over a one cycle, because RMS, so in every half cycle it will be symmetric. So 0 to pi 1 by pi whole root over. Okay. So if you do it, we filter RMS, that will come out to be 116.255 volts. Just check, just to give you acquaintance. I am just making you see this problem. So in this problem, just one thing you need to know, that in a three-phase system, right, you need to know how the, with change in your firing angle, how the waveform can also change. So just basic knowledge. So I have also drawn the waveforms, that you can see that for alpha equal to 60 degree you are just hitting boundary, and then alpha equal to 90 degree you are hitting, beyond alpha 60 degree only you are starting to hit the discontinuous zone, and slowly you are getting lesser voltages, right? So this is for a three-phase controlled rectifier, right? Thyristor based converter, I can write thyristor based rectifier. And I already told you that what will be the value of. So what it is asking, just see the problem. Problem are read, right?
Yes, sir.
So what it is, yes, what it is asking, it is asking to calculate RMS value of the AC supply. So as you understand, as you change alpha, your average voltage or RMS voltage all will change. The output voltage. So what I am telling, you need to have an expression for which you want to calculate the average voltage with respect to changing alpha. So that is what we are going to understand, that with changing alpha, how your waveforms are changing. So I have given the explanation. You can just go through and let me know if you have any doubt. So I will give you the expression, okay? To determine the filter current, right, for harmonic compensation. Please read the line. What they are asking, that filter current for harmonic compensation. So harmonic compensation means that harmonics RMS current, I harmonic RMS, you need to calculate. So for that you need to calculate IS fundamental and IS RMS. So IL RMS is nothing. So RMS value I can tell you, and RMS fundamental value. Both we need. Okay. So RMS value is given by is of load. Okay. And RMS fundamental of load current. So first I want to give you the RMS value of load current, that is IL, and then I will give you IL1. So this is Vs by R 2 pi plus 3 root 3 cos 2 alpha by pi. Whole to the power half. Screen is visible, right?
Yes, sir.
So please note this down, that RMS value of the load current you can get from here. So as you can understand, the load current will completely depend on alpha because voltage is already changing with alpha. And RMS value of fundamental component of load current. There is all we are talking on the AC side, right? Not DC side. So after this you have IL1 AC, fundamental of load current AC component, Vs by 2 pi R into 3 root 3 sine 2 alpha whole square plus 2 pi plus 3 root 3 cos 2 alpha whole to the power half. One second. Whole to the power half, right? So this is half, please note, okay? Or I can just write like this to avoid any kind of confusion. Okay. Just let me check. Yes, it is correct. So if you see IL1 AC, that is fundamental of load supply side reflected load current, AC side I can tell, is coming if you plug the values of alpha is 45 degree. If you plug all those values and Vs you know, R you know, all are given in the problem, right? 12 ohms. If you plug these values, the load reflected, that is supply side or AC side reflected load fundamental component is by this formula, RMS component will come out as 24.973 amps. And your AC side RMS load component overall will come out as 27.217. So if you find the difference, then you can find I filter harmonic currents root over IS square minus IS1 square. Why I am writing IS here? Because your IL1 will be supplied by IS1. So both are same only. And IS is nothing but, since all are series connected, your IS and IL will be same because these all supply side reflected. Get my point? Hello?
Yes, sir. Yes, sir. Yes.
So net current is actually whatever is the supply current or whatever is the load current, I can tell IL minus IL1 is the harmonic current. Harmonic current will be absorbed by the filter only. And otherwise all are in series connection. So the supply fundamental and your load fundamental will be same. So IL1 is IS1 and remaining harmonic current will flow into the load will flow into the filter. So that is how we are determining. So 27.2 square minus 24.97 square whole root over. And it is coming as How much is it coming? I filter harmonics 10.82, right? So 10.82 amps. And if someone asks you what is the fundamental of supply, then it is same as the fundamental of load, and fundamental of load is nothing but 24.973. So this can also be asked. Okay, why the fundamental of load and supply are same? Because it is already given in the problem that it provides harmonic compensation and obviously reactive power compensation. So it is UP, kind of UP of operation. Okay, so fundamental obviously should be same. Fundamental of load and fundamental of your supply, because the harmonics are compensated already. So remaining active component needs to be pushed from the supply side. And another small problem which I want to deal is a 4-wire problem, which I had already. This one. Just I will take 2 more minutes. Okay. Just see this problem. It is useful for you. Everyone seeing na? I can just see. Someone is there in the session, right? Okay. So problem is visible, right? On the screen.
Yes, sir.
Just read this problem. It is important. Then we can wrap up the complete this series filter and your shunt filter active and passive. It will be complete. It is a 2-line problem. Okay, just see this. We will finish within 2 minutes. So the last part I have to rush through. If someone has any specific doubts, he can always contact me. Okay, he or she, they can contact me. Just see this. It is useful problem. So it is a 4-wire problem where you have 3 single phase loads. Okay, connected between phase and neutral. We have done these kind of problems, but only difference is that if you have to calculate. So we have deployed shunt active power filter for harmonic compensation at unity power factor, and obviously for reactive power compensation also, and calculate the RMS value of the filter for harmonic current compensation. So in order to do such kind of problem, you know that single phase loads, that is thyristor based loads, constant current, constant DC current loads, they all have square wave nature, I told you, which toggles between plus 30 and minus 30, given 30 ampere DC. So since it is toggling, we can find out I RMS fundamental is 2 root 2 by pi into IDC. DC is 30. Screen visible, right? Hello?
Yes, sir. Yes,
And
yes.
no lag is coming, right?
No, sir, no.
Okay. So 27 is the fundamental RMS. Okay. Done up to this?
Yes, sir, yes.
So what is the RMS fundamental? This is the RMS fundamental, right? But you see that I have fired at 30 degree, right? So there is a displacement power factor of 30 degree, cos 30 degree. Since your waveform is shifted compared to the voltage, please understand your waveform is shifted by 30 degree. This is your amplitude, 30 ampere minus 30 ampere, and 30 degree shift will come because you're triggering the thyristor at 30 degree. So your fundamental is 27, 2 root 2 by pi IDC. But this is active component, okay? Since this came from the power balance. So actual RMS fundamental is nothing but 27 by dPf. It's 27 by cos alpha. Sorry, one second. So this is the, I am telling whatever this is the actual RMS, right? So one second. This is RMS fundamental, right? But what you see, whenever you determine this RMS component, your waveform, fundamental waveform is shifted by 30 degree, right? Agreed or not?
Yes, sir.
This is 180 degree. From alpha to 180 plus alpha. So 180 plus, so alpha shift is there, right? Cos alpha. So if you want to find out the active component of load current, I can tell. Active component of load current is IS1 cos alpha, which is 27 times cos alpha. Because whenever you do the power balance, you write like this, that 3 times, or for single phase you can write VRMS phase 1 into IRMS phase 1 into cos alpha is the active power, is equal to whatever is the output voltage. So for your three phase, because they are all single phase loads, so what is the 2 Vm by pi? 2 root 2 into Vs RMS phase 1 by pi cos alpha into 1, your IDC. So I RMS phase 1 equal to 2 root 2 by pi, whatever we were doing, into VRMS gone, so IDC. So this was actually the what? Not active component, RMS component. Agreed or not? Because your power is what? VRMS into IRMS into cos alpha. So this was the RMS component, not the active component. So to find the active component, you have to multiply with cos alpha. That is what I am trying to tell. So 27 into cos alpha. Cos alpha is cos 30 degree. So what is this? 23.39 amps. Now, I told you that such square waves for 180 degrees, 120 degree shifted, because for 3 phases you will have 3 120 degree shifted voltages. Agreed or not? Then such square waves will also be 120 degree shifted. Then sum of such square waves, because this is a 3 phase 4 wire system, then I neutral is what? I neutral is ISA plus ISB plus ISC. So such square waves, 180 degree square waves, when 120 degrees shifted, if you add, then you will get also neutral current will also be squared in nature with 3 times frequency, 3 times fundamental frequency. So it will be toggling much faster at a faster rate, but between same plus 30 to minus 30. So please be careful that sum of 120 degree shifted square waves is also a square wave, not like sine that it will be 0. What the concept? Hello?
So, but how did you get this 120? Our alpha was 30, right?
No, alpha was 30. I am telling this for a single phase. Now you have 3 such phases.
Okay,
Connected to
okay,
each
okay.
of 3 such single phase loads connected to each of the phases. So this was analysis for only one phase. So for all the other 2 phases, such square waves will be there. This was for
Yes.
one phase. Such
Yes.
another phase 120 degree shifted because voltage become 120 degree shifted for other
Okay.
phase. Then
Okay.
for another phase 120 degree again shift, and you sum them up and form the neutral current, which will again be 30 to minus 30, but 3 times the frequency. When you, I also solved in week 1 and 2 also, that it came the square wave neutral current.
Okay.
Yes. So what is the filter current? Filter current is nothing but Is square minus Is1 square. So Is, you know, what is the value of Is? And Is1 also, you know, Is1 is 27 and your Is is 30 because RMS of square wave is 30 only, minus 30. So Is is 30 square minus Is fundamental RMS. So this is coming as 13.057. This is I filter RMS. And someone asks you to calculate KVA rating of the that is the shunt APF, then what will be KVA rating? Can anyone tell me? So please
Root 3 into
be
root
cautious.
3 into V into.
No. No. This is 4-wire system. So you do per phase. 3 times V filter into I filter for each of the 3 phases. Agreed? Plus V filter into V filter per phase. Okay. Into I neutral. All RMS. KVA. Okay. This is by 1000 obviously if you write in KVA. So what is 3 times V filter into I filter per phase? I will just rub and write. So 3 times V, this is 400 by root 3 into I filter RMS. I filter RMS I calculated just now. What was it? 13 from here. Plus V filter RMS into your load current. Okay. Which is in this case 30. Your neutral current, which is square. Okay. This will be your filter current for the 3 phases, and for the neutral the current will be like this. So neutral compensation it needs to do, right, to provide the, it is mentioned here at unity power factor harmonic current, harmonic compensation. Okay, so to provide the path for the neutral current it has to circulate it, so its rating should be like this, that the 4th wire should be carrying 30 amps. So this should be the volt ampere rating. So like that you can calculate actually the KVA rating. Okay, so this is only thing I wanted to cover because it is useful for your assignment also, right? Other than that it is okay. Okay, so it is the thing, you can just see this and nothing
Okay.
else. So,
Okay,
yes.
sir.
Okay.
Thank
You
you
can
so
just read the session.
much. Sir, can we request the team to upload the solutions for previous week's quizzes?
Yes, we have already provided the solution. You can just mail the NPTEL team because they only have the right to upload the solution. So you can mail them. We have already provided solution.
Okay, sir.
Just send a mail requesting them to upload the solutions. Okay.
Okay, sir.
Okay. Thank you.
Thank you, sir.